Hello everyone, welcome to Scottish Summit 2021. Good morning, good afternoon, good evening, depending upon where you are joining today. My name is Deepthi Goguri. Today we are going to discuss on the topic SQL Engine, its working style. So this session is all about SQL Server internals and architecture. There is a lot of content to grab, so hopefully you like it. Let's get started. First of all, a big shout out and thank you to all of our sponsors ScriptRunner, DQ Global, Driving Data Quality, Proximo 3, Red Spire, Agilicis, and Hitachi Solutions. Without your support, this Scottish Summit 2021 is not at all possible. Thank you so much for all of our sponsors. A little bit about me. I'm a database administrator having several years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology at Eastern Illinois University. I blog for dbanuggets.com, that's my website. And you can contact me on Twitter at dbanuggets, that's my user ID. I'm very active on Twitter, so I would love to connect with you guys. So if you want to contact me via Twitter. So what are we going to discuss in this session today? We are going to see the basics. First, the basics, the asset properties. Then we are going to discuss about the different types of components we have inside the memory architecture of SQL Server. Then in this particular session, we are mainly focusing on the major components of memory architecture, that's plan cache and the buffer pool, and how does these cache get managed inside SQL Server. And then we are going to see the life cycle of a query for the read as well as the write transactions. And we are also going to see the different types of components we have inside the SQL engine. That's the components of the storage engine and the components of the relational engine. So internals, why should we care, right? Many DBAs and developers, they work with SQL Server on daily basis, but they might not exactly understand what happens behind the scenes when we submit any query until we get the results on our screen. So knowing this information will really help you in understanding how queries are processed at each stage inside the SQL engine. It will also help you in tracking down the performance issues very quickly and fix them efficiently. It will also build you confidence while managing the database engine as well as the databases. It will also help you in convincing your managers and co-workers of why they have to take your ideas seriously, because by the end of this session you will come to know how the SQL Server will do the processing behind the scenes when you submit any query. This particular information is very helpful while suggesting some of the critical information to your managers or co-workers of why they have to take your ideas. Last but not least, we work with SQL Server every day, so the more we know about the internals, the better we can understand how SQL Engine works. Let's start with the basics, the asset properties. Every major relational engine, it can be the SQL Server, Oracle, PostgreSQL, all these major relational engines should satisfy the asset properties of transaction. So what is this asset? A stands for atomicity. Atomic meaning a single unit of work. A single transaction can contain one operation in it, or it can contain multiple operations in it. All the operations inside the single transaction should either complete successfully or none of them. Let's take an example of a store procedure. Inside the store procedure, let's say we have two operations, an update statement as well as an insert statement in it. Whenever we execute the store procedure, both the operations should either complete successfully or none of them. For example, if the update succeeds and if the insert fails, then the SQL Server should go ahead and roll back the entire transaction. That's atomicity. C stands for consistency. The data inside the database should always be consistent before starting the transaction and after completing the transaction. Let's take an example. I wanted to do an update statement on a table, and while I'm doing that update, if something happens suddenly, like if there is a power outage and if we had to restart the SQL Server, once we restart the SQL Server should roll back this particular uncommitted transaction, making the data in the consistent state. That's consistency. I stands for isolation. No matter how many concurrent transactions are happening at the same time, each and every individual transaction should be independent of each other and should not be interfering with any other transaction. Let's take an example like I wanted to insert a bunch of records into a table. While I am doing that insert, none of the other transactions which are running concurrently should even know that I am inserting data into a table. That's isolation. D stands for durability. Once the transaction has been successfully completed and all the data that has already been made to the database should be permanent. Like later, if I had to restart the SQL Server, once the data has been committed to the database, it should not lose, right? Once even we restart the SQL Server, there should not be any data loss in the database. That's durability. So what components of SQL engine will ensure this asset property? Atomicity is very easy to be ensured. It is taken care by the parse component inside the relational engine. Consistency is also very easy to be ensured. It is taken care by the parser and binder components inside the relational engine. Isolation is all about the locking mechanism. It is taken care by the lock manager inside the storage engine. Durability is the most toughest of all. It is taken care by the transaction log inside the storage engine. Let's take a very simple example ensuring this asset property. Let's take a very simple bank transaction, right? For example, I have a balance of $500 in my account, which have an ID of 1, and I would like to send $100 as a gift to my friend, which have an ID of 2. I can do this simple bank transaction multiple ways, right? I can use the online application to do it, or even I can use the mobile phone application to do it. So for this example, let's take the mobile phone application. So once I begin the transaction on my mobile phone, behind the scenes, SQL Server will also begin the transaction. It will first go ahead and do the first operation, which is to deduct $100 from my balance, which will makes the $400, right? The first operation is completed now. And thus in the same transaction, we have a second operation that is to credit $100 to my friend's account, right? But I suddenly see this on my screen. While I still did not complete my transaction, I see I am logged out of the mobile phone application and I see this alert saying facility is temporarily unavailable. Now wait, what? What has happened? I mean, between the transaction, my transaction is not completed yet. So I do not know what has happened. I'm very angry on the bank guys, literally. So I immediately called my friend to ask if she received any money, which she said she didn't. So I immediately called bank customer service guys to know what has happened to my money. They said there was a severe thunderstorm and some of their SQL server went down and they already restarted them. So if this particular transaction is ensuring the asset property, right? What should happen? Let's see what will happen once they restarted the SQL server. Once the SQL server restarts, that particular uncommitted transaction, which is stopped in between, right? It is completely rolled back, making the data in the consistent state. Now, this particular transaction is ensuring the asset property. Now, how? Atomicity is ensured by rolling back the entire transaction. Consistency is ensured by reflecting $500 in my balance, which is the initial amount before beginning the transaction. So consistency is also ensured. So how about the isolation? Isolation is also ensured. Like, did you observe when SQL Server went ahead and deducted $100 from my balance? None of the other transactions have been interfering with my transaction. And the durability is also ensured. There is no loss in my money, right? I still have $500 in my balance. That's how each and every transaction of all these relational engine should satisfy the asset properties of transactions. Now let's talk about the SQL Server memory architecture. SQL Server Engine is a Windows program which will use Windows APIs to allocate memory to the SQL Server. Now there are different components we have in the memory architecture of SQL Server. But in this particular session, we are mainly focusing on the plan cache and the buffer pool. But let's go ahead and see what all components we have here. First component, the plan cache, it's one of the biggest components. It stores the store procedures, query plans, etc. The buffer pool, which is the biggest out of all, it will hold the 8 KB data pages and the index pages in it. There are also other type of cache like log cache, token and perm user store cache. Now what this token and perm user store cache does is it will store the user permissions onto the objects. There is also other type of cache known as column store cache, which will hold this column store indexes in it. Now all these caches which you are seeing in the blue color are very special. Now why I say that? They are very special because they have a backing mechanism in them and they can be easily expanded and shrinked when there is a memory pressure. But what about, like, let's talk about the backing mechanism, right? Like, what is this backing mechanism and why they are so special? Let's talk about the plan cache. The store procedures which are saved inside the plan cache, the query text behind that store procedures are stored inside the system tables. Let's talk about the buffer pool. The data pages which are stored inside the buffer pool, these are backed up as the database files inside the disk subsystem. Like the log cache is stored as a transaction log inside the disk subsystem. And the column store indexes, which are stored inside the column store cache, these column store indexes are compressed and they are also stored inside the disk subsystem. Now that's when, like, when there is a memory pressure, they can be easily expanded and shrink, right? But what about the fixed memory, which is in that green color? Fixed memory is known as fixed because it cannot be expanded and shrinked when it is in use. When it is not in use, it can be expanded and shrinked. Now, what kind of things will be stored inside the fixed memory? The connections to the SQL Server, like the memory grant connections for the hashes and so on, those kind of connections are stored inside the fixed memory. There is also other type of cache known as SQL Server.exe overhead cache. This kind of memory will hold the um, SQL Server.exe is an executable and many things will be running this executable, right? Like for example, the thread stacks. There is also other type of memory known as in-memory OLTP, which will basically store the memory optimized tables. And even this type of memory can't be expanded and shrinked when it is in use. So there should be some other cleaning up process should come and clean up all these memory optimized tables in it such that it will have more memory for the new objects to be stored. That's just an overview of SQL Server memory architecture. Now let's go ahead and talk about the plan cache and the buffer pool. How do they get managed? How does this memory gets managed inside SQL Server? There is something known as LRUK algorithm, which is also known as least recently used algorithm. The hyphen K is for the complexity of the code. Now what is this LRU? LRU meaning if something is staying inside the cache for the longer time, those kind of things will be discarded first. Like if they are not being used, those kind of things will be kicked out first. Now how does this get managed, right? How does this memory gets managed? For the plan cache, there are two processes which will manage the plan cache. One is lazy writer and the other is ghost cleanup. Now let's go ahead and talk about how these two processes works. Now this is my plan cache, the right side diagram you see. We just have three execution plans in it. The plan 1, plan 2 and plan 3. Whenever the sorry, I forgot a step here. So there are two types of numbers at the bottom of each object. The left side number is known as complexity code value and the right side number is known as complexity countdown value. So these two numbers are there on each and every object. Now whenever the lazy writer will get kicked in every minute by the SQL Server automatically, what this lazy writer do? The lazy writer will go ahead and check if there are any least recently used execution plans. If it finds them, it will go ahead and decrement the complexity countdown value of it by 1. So here none of them will be used. So the lazy writer will go ahead and decrement plan 1 complexity countdown value from 18 to 17, for the plan 2 from 9 to 8, and for the plan 3 from 2 to 1. And the lazy writer will go away. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. Here, none of them will be used again. So the plan cache, lazy writer will go ahead and decrement the plan 1 complexity countdown value from 17 to 16, for the plan 2 from 8 to 7, for the plan 3 from 1 to 0. Now did you observe here? The complexity countdown value for the plan 3 has turned to 0. That means the SQL Server should go ahead and evict this plan out of the cache, right? But that is not what it is going to happen. There is some other process which is known as ghost cleanup, which will be kicked in every couple of minutes by the SQL Server automatically. Now what it does, it will go ahead and check if there are any objects that doesn't have any countdown value. Once it finds them, it will go ahead and flag them as ghosted. That means they are still inside the plan cache, but they are in the offline. Like if there is a memory pressure tomorrow, then the ghost cleanup on its regular process, it will go ahead and flush these ghosted execution plan out of the cache. But what if there is no memory pressure? In that case, these plans are still going to stay inside the plan cache, such that there might be other user who might use the same execution plan for their queries. That's how the ghost cleanup process works. In the very next minute, the lazy writer kick back in again to see if there are any least recently used execution plans. Here, the plan 2 will be used. So the lazy writer will go ahead and increment the complexity countdown value for the plan 2 from 7 to its original value, which is 9. That's how the lazy writer and the ghost cleanup will manage the plan cache. Now let's talk about the buffer pool. The buffer pool, it holds 8 KB data pages and the index pages in it. It have to basically manage 3 kinds of different structures: clustered indexes, non-clustered indexes, and heap tables. What if you have a heap table and you wanted to do an operation on it, right? The buffer pool now have to go ahead and grab all those data pages into the buffer pool, do the operation over there, and send the results to the user, which is very IO intensive because the buffer pool has to go many trips to grab these data pages into the buffer pool. But what if you put a clustered index and the non-clustered index on the top of this table, heap table, then that will help the buffer pool now, because now it have to only go ahead and grab the pages in few trips, right? Which will help reduce the IO and speed up the query process. Now, how does this buffer pool gets managed? There is something known as checkpoint process, which will be kicked in every couple of minutes by the SQL Server automatically. Now, whenever it gets kicked in, it will go ahead and check if there are any dirty pages inside the buffer pool. Now, what are these dirty pages? Dirty pages are the data pages which are already modified inside the buffer pool, but they are not yet hardened to the database file system. Now, whenever the checkpoint process kicked in, it will grab all these data pages, dirty pages, and it will flush them into the database file system and harden them onto the disk. That's how the checkpoint process will manage the buffer pool. Now, this is a very important slide, an interesting slide, how the optimizer will choose the plan. As you know, SQL Optimizer is a cost-based optimizer. It always wanted to choose the good enough plan instead of the best plan. Now, what is the difference? The time and the cost is the difference. What if the optimizer wanted to get that best plan instead of the good enough plan? What it have to do, right? Let's take an example here. We have a very simple select statement which have a 4 table join here, and each table have a clustered index and 3 non-clustered index on top of each table. Now what if the optimizer have to go ahead and get that best plan, right? First, it will go ahead and analyze 72 different types of physical access methods per table. That means we have 4 table join here, right? That means 72 times 4, those many physical access methods. Like it have to go ahead and choose whether it have to use the clustered index scan or seek, or whether any lookups needed, those kind of physical access methods, 72 per table. On the top of it, the optimizer have to go ahead and analyze 24 different types of logical join orders. Now what are these logical join orders? Here we have a 4 table join statement, right? What if the join between A to B is filtering out 60% of the records from the result set, and the join between B to C is filtering out around 80% of the records from the result set? In that case, the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C front of the statement and the join between A to B back of it. Now why the optimizer do that is because it wanted to grab the results as quickly as possible. On the top of it, the optimizer have to go ahead and analyze so many transformation rules. Out of analyzing all of them, it will approximately gather 76,000 possible plans. Out of all of them, it will find the best plan. Just imagine how much time and the cost the optimizer have to take to get that good and like the best plan out of all these plans, right? It will take so much time, and no user wanted to wait for such long time to grab his results. That is the reason the SQL optimizer, instead of going ahead and analyzing all of these transformation rules, it will go ahead and analyze some of the transformation rules to get that good enough plan. That's how the SQL optimizer will grab the good enough plan, and that is the reason why it is quick. If we discuss the same information in a very simple words, let's take a simple query, and while we run it, the optimizer thought the execution plan A will be better in 3 milliseconds it found, but execution plan B is also better in 3.5 milliseconds. But if it have to know whether A is better or B is better, it have to go ahead and analyze for 5 minutes. Optimizer doesn't want to do that. It will just go ahead and grab the plan A or plan B randomly. That is how the optimizer will choose the plan. Let's talk about the life cycle of a query. So if the life cycle of a query is divided into 3 different steps, then the first step contains the components parser, binder, simplification, and the trivial plan. These components from the first step are very simple. They are very lightweight to the SQL Server. But when you come to the second step contains the components load metadata, join heuristics, and search phases. Now these components from the second step are they require most of the metadata to process any query. When you come to the third step contains the components access methods, transaction manager, and buffer manager. All these components from the third step are very IO intensive. Now why I say that is because the buffer manager component we have in the third step have to go ahead and grab all those data pages into the buffer manager to do the operations, right? It is very IO intensive. So when you compare the first step and the second step components with the third step components are very IO intensive. Now the first step components and the second step components will come under the relational engine, And the third step components will come under the storage engine. This is just an overview of what all components we have inside the SQL engine. Now let's go ahead and talk about like what happens behind the scenes when a query is sent to the SQL server. Here we have a user who wanted to do a select query onto the SQL server. No matter what kind of interface he is using, he can be using SQL Server Management Studio, Azure Data Studio, .NET Visual Studio, or even a third-party application. No matter what kind of interface he is using, he should first get the secure network connection to the SQL Server. Now, how do he get that? There is something known as SNI, which is also known as SQL Server Network Interface. SQL Server Network Interface, what it does is it will use the internet protocols to establish a secure network connection to the SQL Server. Once the secure network connection has been established, the query that the user is sending, that particular query is wrapped inside a tabular data stream packet, which is also known as a TDS packet, and that TDS packet will be now sent to the SQL operating system. Once the TDS packet has reached the SQL operating system will first identify that coming connection as a SQL connection, and it will assign a SPID to it. You know SPID, right? SP who do, SP who, whenever you execute, you see those SPIDs, SPID number 75, SPID number 94. Those are the active connections which are made to the SQL server. Once the SPID has been assigned, now the TDS packet will be unwrapped and that particular query is identified as a SQL query. Now that particular query will be sent to the first step inside the relational engine. So the first component inside the first step of relational engine is the parser. Parser, it will just identify and validate the syntax of the query. Like for example, I wanted to do a select star from a table, but by mistake I have given select star from. In that case, the parser should first identify that as a syntactical error and throw back me an error saying it is syntactically incorrect. And variables are declared at this component, like whether you are declaring variables properly or not, those kind of things are checked here. Views are expanded here. Like if your query is having any views, the query text behind those views are brought in line into the code you are sending. So the views are expanded. And now with all this information, the parser, it will go ahead and check if there is an exact match of the execution plan for that query inside the plan cache. If it finds the exact match of the execution plan, it will go ahead and use the same execution plan for the execution phase. But what if it didn't find the execution plan, right? It will go ahead and build the initial logical tree for the first time. Then our query will be sent to the binder component. Now with the binder component, binder is also known as algebraizer or the normalizer. What happens at the binder component is it will go ahead and check the user permissions, like whether the user that is running the query, whether he have enough permissions to those objects or not. Binder component will validate the objects like the columns, tables, whether they are valid or not. Parser will just identify the syntax, but the binder is the one which will validate the objects. Data type resolution happens here. Like if you are using a select statement and you are using union all clause between two tables in those select statement, the ordinal columns of those two tables should match in their data type. If that doesn't match, then that will cause a data type resolution error. Aggregate binding also happens here, like sum, average, those kind of things are bound here. With all this information, the binder will go ahead and update the parse tree inside the plan cache one more time, and the query will be sent to the simplification component. As the name itself says, simplification will simplify the query. Now, if there are any subqueries in your query, those subqueries are converted as a simple join behind the scenes by the simplification component. Now, Contradiction detection also happens here. Like if you have any foreign key contradiction, those kind of contradiction are detected here. And with all this information, once again the parse tree inside the plan cache is once again updated, and then our query will be sent to the trivial plan component. Now, if our query is so simple, like select star from or a select star from a table with a where clause, those kind of queries are treated to be very simple by SQL Server, and SQL Server think this way. Hmm, why should I even consider the query tree that has been already built inside the plan cache until now? I do not wanted to consider that. Let me go ahead and discard that parse tree inside the plan cache and build a trivial plan on the fly, because SQL Server, it doesn't cost it much to create these trivial plans. It doesn't take any resources to build these trivial plans, and these trivial plans by default are not stored inside the plan cache. So once these trivial plans are being built, those trivial plans will be sent to the execution phase. But what if our query is not so simple? What if our query has 10 tables in it with a complicated logic in it? Then those kind of queries are treated as complicated, and the SQL Server wanted to build full tree for that, full plan for that. In that case, the query will be sent to the second step of the relational engine. So the first component inside the second step of relational engine is load metadata. Most of the metadata to process any of the query are gathered here, like the index statistics and histograms are gathered here. These statistics are the blob structures which are saved inside the system tables to describe the distribution of the data inside a column or set of columns or an indexed view. So basically the optimizer have to trust these statistics to determine how many rows it can think coming out of a table or a column to get those memory grants for the queries. Those kind of information are gathered here. Auto create stats happens here. If at all you are running a query very frequently and you are searching on a column and that column is not in the key column of an index, then SQL Server will go ahead and auto create stats on that particular column. SQL Server and Windows collation are checked here. Like set options are also checked here, like set XML on or off, set ANSI padding on or off. These kind of options are checked here. Now with all this information, the parse tree inside the plan cache is once again updated. And then our query will go to the join heuristic component. Join heuristic component will reorder the join. Like if our join in a query from join between A to B is filtering out around 70% of the records from the result set, and the join between B to C is filtering out around 99% of the records from the result set. In that case, the SQL Server will go ahead and reorder the join in such a way that it will push back the join between B to C front of the statement and the join between A to B back of it to grab the results as quickly as possible. Now, with all this information, once again the parse tree inside the plan cache is updated, and then our query will be sent to the search phases. In the very next slide, we are going to discuss what these search phases are. But for now, just remember that the optimizer is a cost-based optimizer. It always wanted to get that good enough plan, right? It will get that information from these three phases. Once it gathered that information, it will go ahead and update inside the parse tree, inside the plan cache, and put a hash finally on that particular query plan, and then send the query to the storage engine component. But before going into the storage engine component, let's see what these search phases are. Now no matter what kind of query we are sending to the SQL Server, the optimizer have to go ahead and grab that execution plan information from these three phases. The phase 0 is known as transaction plan. These kind of plans are created at the pre-optimization stage. Now, what is this pre-optimization stage? The first component inside the relational engine, the parser, binder, simplification, and the trivial plan, those components will come under the pre-optimization stage. That means trivial plans are generated here, right? And these trivial plans are created as quickly as possible. They are created for the small queries with maximum of 3 tables in it. Very basic heuristics are needed to create these execution plans. But what about the phase 1? Phase 1 is known as quick plan. These execution plans are created for the queries with maximum of 8 tables in it, and more transformation rules are needed than the phase 0. When you compare the phase 0 and phase 1, when you see the phase 0 and phase 1, the optimizer, it will go ahead and take the query and compare our query with already existing execution shapes. If it finds a good enough plan, it will go ahead and use the same plan for the execution phase. But if that is not the case with the phase 2, phase 2 is known as full plan. Now these full plans are created for more complicated queries like parallelism, spills, and spools to the temp DB happen at this phase 2. Almost all the transformation rules are unlocked here. Now what the optimizer does is, it will first go ahead and prune off all the transformation rules it doesn't need. Let's take an example of a query. For example, if that query do not have a varchar max data type, in that case, the optimizer will first go ahead and prune off all the transformation rules which are related to that in varchar max, such that it can go ahead and analyze only some of the transformation rules to get that good enough plan. That's how the optimizer have to go ahead and get that information from these 3 phases. Now our read transaction is at the storage engine component, which is the third step, right? But before going into the storage engine, depending upon the complication of our query, all the queries have to pass from the first step, second step, and the third step. If our query is so simple, then the trivial plans get generated at the first step, and then the query will be sent to the storage engine component. If our queries are really complicated, then they have to pass through the second step of relational engine and then to the third step of storage engine. Now, for the read and the write transaction, all the difference happens at the storage engine component, at the transaction manager and the buffer manager components especially. So the first component here, access methods. Access methods component by itself, it doesn't perform any action, but all it have to do is to analyze how it have to grab the results from the disk subsystem. Once the query has to go ahead and go to the transaction manager component. Transaction manager component have 2 subcomponents in it, the log manager and the log manager. But as this is a read transaction, we need to just invoke the log manager part of it because we are not modifying any of the data, right? So the transaction manager will go ahead and request the buffer manager to put a shared lock on the resources it needs. Once the query has reached the buffer manager component, buffer manager will first go ahead and put the shared lock on the resources it needs because this is a read transaction, right? And then go ahead and check if all the resources it needs are already inside the buffer pool. If it didn't find any of them or all of them, it will go ahead and grab those pages in the form of 8 KB pages, put them in the buffer pool, do the operations over there and send the results to the user. Read transaction, very simple. But what happens with the write transaction? Access methods by itself, it doesn't perform any action, but all it does is to grab the results from the disk subsystem, right? It have to analyze. Once the component has reached to the, once a query has reached to the transaction manager, now as this is a write transaction, before writing any data into the database pages inside the buffer pool, those changes have to be written to the transaction log. Once those changes has written to the transaction log, those that particular transaction manager will now invoke the log manager part of it. As this is a write transaction, transaction manager will go ahead and request the buffer manager to put an exclusive log. The exclusive log is because we do not want it to interfere with no other transaction have to interfere with our transaction, right? So once the query has now reached to the buffer manager, first the buffer manager will go ahead and put the exclusive lock on the resources it needs, and then go ahead and check if all of the resources are already inside the buffer pool. If it didn't find some of them or any of them, it will go ahead and grab the pages in the form of KB pages, just like the select statements, right? Do the operation over here, do the modification over here, and send the success message to the user. That's how the write transaction works. But did you observe something here? The the database pages are already inside the buffer pool. They are modified, but they are not yet hardened to the database file system, right? The dirty pages. That's when the checkpoint process will kick in and then grab all these dirty pages from the buffer pool and harden them onto the database file system. That's the write transaction, how they work behind the scenes. Now let me go ahead and do a very quick demo to show you uh, how the pre-optimization stages works. Now for my demo, we are using AdventureWorks 2016 database. And let me show you first how the parse only option works. Let me go ahead and set the parse only option on. We can do that by using the set parse only option on or by enabling this parse only button inside the management studio. Let me go ahead and do a very simple select statement. It ran fine because there were no syntactical errors. But this time, I'm not declaring the variable, but I'm using the variable in the where clause. When I execute that, it should throw me an error. Must declare the variable. Let me go ahead and do a very simple select statement. Select non-existing column from a non-existing table. When I execute that, it should not throw me an error because this is just the parser, right? Syntactically, this is correct. Let me go ahead and set off the parse only option off. Let me go ahead and set the format only option this time to be turned on. Now when I turn this option on, it doesn't produce any results or it doesn't generate any execution plan. But all it does is it will invoke the parser as well as the binder components together. Now the format only option is deprecated, but we can still use it until they completely remove it, right? Let me go ahead and do a very simple select statement which do not have any syntactical errors or all the objects in it, columns, tables are valid. So when I execute that, it doesn't produce any results. Run fine. But this time when I execute the same query, select non-existing column from a non-existing table, when I execute that, now the binder component will be kicked in and it will say invalid object name. Let me set the format only option off. Let me show you how the data type resolution works. Here we are using union all clause between two tables, doing a select statement between those two tables. The ordinal column of those two tables should match in their data type. The customer ID is of an integer data type and the sales order ID is also of an integer data type. So whenever I execute that, it should produce the results, right? But what if I manually created a data type resolution here? The customer ID is of a integer data type and the sales order and the credit card approval code is of a varchar data type this time. Since both are not compatible, when I execute, it should throw me a conversion failed error. That's how the parser and the binder component will work together. Now let me go ahead and see how the simplification and the trivial plan components work. Let me go ahead and use the same AdventureWorks 2016 database here. Let me go ahead and run this particular query, which have a simple subquery in it. As you know, the simplification should simplify the query by converting the subqueries into the simple joins, right? Let me go ahead and enable the actual execution plan on and execute the query. When you go to the execution plan, here it has actually converted that subquery into a very simple inner join. That's how the subqueries are converted behind the scenes. Let me go ahead and show you how the redundant joins will be used. Here we are only grabbing the results from the sales order header table, but we are simply using the customer table here. So when I execute this, SQL Server will go ahead and only get the results from the sales order header table. Now if it did not use the sales order detail table at all. Now if that is a different join, right? For the left join we are not going to use any left outer, but if that is a inner join in or any other join, if these two tables are having relationship between them, like foreign key relationship between them, then even though you are using the redundant join here, the table, SQL Server will go ahead and trust the relationship and then discard that table in the execution plan. It doesn't use it. But if there is no relationship between those two tables, then SQL Server should definitely go ahead and use both the tables inside the execution plan to check those values, right? Let me go ahead and show you how the contradiction works. Here I created a manual contradiction where territory ID is equal to 1 and where territory ID is not equal to 1. So when I execute that, it should not produce any results. Let me go ahead and show you how the trivial plan works now. This is a very simple select statement. Let's go ahead and see if the SQL Server will create a trivial plan for it. I'm in the execution plan, to the properties. Did you see the optimization level here? It has created the trivial plan because this particular query is so simple. Select statement with a very simple where clause. It created a trivial plan. But what if you wanted to convert this trivial plan into a full plan and you wanted to save that plan inside the plan cache? This is not at all advisable to do it in the production because there is a reason why SQL Server is creating the trivial plan, right? Because it doesn't cost it much, and that is the reason like it can create it as many times as it wants because we are not even saving them inside the plan cache, but there is an option to convert this into a full plan so that that plan will be saved inside the plan cache. But um, I do not suggest you to do this in production. So we can enable the trace flag 8757 to the inside the query. When you run this query with the trace flag, it only bounds to that particular query. It doesn't affect the server or the database level. So when you execute that and check the execution plan to the properties, here this particular query has converted that plan into a full plan. Now this plan, the same execution plan, has been converted from the trivial to the full. So now this particular full plan is saved inside the plan cache. That's how the trivial plan and simplification component works. Let me go ahead and share my slides back again. Now what we have seen in this session today, we have gone through the overview of asset properties and we have seen with a simple example ensuring the asset properties of transaction. We have seen the different types of memory architecture components we have inside the SQL Server, and mainly we have focused on how the plan cache and the buffer pool gets managed, and we have seen the life cycle of a query for the read as well as the write transactions. And we have also seen the different types of components we have inside the SQL engine. That's components of relational engine and the components of storage engine. In order for me to prepare for this presentation, I have followed these resources. If you wanted to know more about the SQL engine, please follow these resources. And I would like to thank all the sponsors, organizers for giving me this wonderful opportunity to present for Scottish Summit 2021. Thank you so much, each and every attendee, for attending all of the sessions. Thank you so much and for giving me this valuable opportunity. This is the time for me to, if you, this is the time you can ask me the questions. Thank you.